So we have seen already two methods to prepare aldehydes and ketone. One is from alcohol oxidation, and here's a primary alcohol. You will oxidize it to an aldehyde with mild oxidizing agents. Here, that PCC, DMP, DMSO. And if you're oxidizing a secondary alcohol, you can use any pretty much oxidizing agent, including John's, and that will be oxidized to ketones. So that's the first method that we saw. Then we studied, and again, you can always look back to that video. So the second reaction that we did is the alkenosynolysis. So alkenes is the double bond, and depending on the substitution of that double bond, when you cleave these, you're going to get the type of products that you want. Aldehydes or ketones. In this particular case, if you do here O3, EMS, you're going to get 2 moles of acetaldehyde. Now, there is a third method, very useful, and this is from alkyne hydration. Alkyne hydration. That hydration, we're going to see that can happen, but Markovnikov and anti-Markovnikov, and depending on that, you're going to get, say, different products. So let's start with a terminal alkyne. Say that I have, let's see, I'm not getting much ink here. So 3. I'm going to say that is terminal. Remember, there will be an H here. So if I do, in first instance, say that I'm using a borane, but this time I'm going to be using, say, Br2H. So R meaning alkyl groups, and I'm transferring 1 hydride. So typically bulky groups. So when you do that, and then so hydroboration followed by oxidation. So that reaction follows the anti-Markovnikov path, which is you will add the H at the more substituted carbon. So what I think is a good idea to remember is that this is anti-Markovnikov and draw the enol intermediate. It will not stay there, but you will know where to put the oxygen at the end. So if I remember this is anti-Markovnikov, then I will put the H here and the OH here. With that in mind, let's draw the product. So I'm going to do, now that I added that across the double bond, I'm going to have the triple bond, I'm going to have a double bond here. So R, and I'm going to get here H, and now here OH. And I'm going to draw the hydrogen so that we keep track. There was a hydrogen here in the terminal alkyne. Yes? And so here I will have OH. I forgot the O. Very important. So this compound, this is an enol, and that's an intermediate. That tautomerizes quickly to the aldehyde. But what I want you to see when you're predicting products is, again, first step, remembering that when you use borane, this is anti-Markovnikov, so you will put the H at the more substituted carbon of the 2 here in the alkyne. Second, once you have the enol, the tautomerization will happen to give you a carbonyl compound. Since the OH is at the terminal carbon, you're going to get an aldehyde. So you're going to get the following here, not drawing the mechanism of the reaction. So that is an aldehyde, not drawing that H here and not the other H. So in here, this is an aldehyde. And not drawing the mechanism. So what I want you to see is to be able to predict products. Remember, the hydroboration again is anti-Markovnikov, H of the more substituted, OH of the least substituted. That will give you the form of the enol, and then check out that the oxygen is at the terminal carbon. So you will get an aldehyde. This is a tautomerization. Okay. And so let's do what will be the terminal alkyne hydration, but with Markovnikov condition. So let me say this one here was anti-Markovnikov. This one here with borane. And now I'm going to do similar. I'm going to do a hydration. Notice that when you're adding OH and H, it is a hydration. You're adding water to the triple bond. Now I'm going to start with again, the terminal alkyne. And this time we're going to be using sulfuric acid. And we also need to use, in the case of alkynes, we need to use mercuric HESO4, mercuric sulfate. Okay, so that is a condition. When you see that this condition is Markovnikov. So what you need to remember when you're predicting products, if this is Markovnikov, what that means, the regioselectivity is that you will put the H at the least substituted. And how do you know it's the least substituted? You don't have an R group here. That's the least substituted. So I'm going to add across the double bond Markovnikov fashion. So the H at the least substituted carbon and the OH at the most substituted carbon. So Markovnikov, anti-Markovnikov. And so in doing that, I'm going to draw the enol, corresponding enol. I'm going to draw my double bond, and I'm going to have the OH here and R here. And I will have an H and an H, so this will be like that, H, H. Typically, you simply will see only this. Let's say this is equal to that. That is also an enol, so all for the OH function group and enols for the alkene, right? This is another enol. But notice that this time the oxygen is not at the terminal carbon. It is in the inner carbon that has the R. For that reason, this will tautomerize. In equilibrium is shifted to the keto form. So you will put the double bond oxygen here, and that's a metal, and that's an R. So that is a ketone. So not drawing the mechanism of tautomerization, but again, what we need to remember when you're predicting product is that condition terminal alkyne, anti-Markovnikov, you put the H at the more substituted, the OH at the least substituted. Draw the enol, and once you draw the enol, all you need to figure out is that the oxygen is at the terminal carbon. So in the tautomer, you will have an aldehyde. And when you do the Markovnikov hydration of the terminal alkyne, then H at the least substituted, OH at the more substituted. And that will determine the enol. So you do your double bond. OH is now not at the terminal carbon, it is in the internal carbon. So you will end up with a ketone. And this two equilibrium favored what we call the keto form over the enol. So that's another way of making aldehydes and ketones from the hydration of terminal alkynes.